Oh, Russell, you hound. Let's see what we have today. Looks like today we'll be starting with section 3.2 on differentiability, of how the derivative of a function might fail to exist. Now, for the time being, we're going to put aside that Euler's method isn't around because, well, between you and me, that chap didn't have it all in the ball. But we'll be learning about the regions at where it might fail to exist, such as a corner, a cusp, a vertical tangent, or possibly even discontinuity. And secondly, we'll be covering derivatives of trigonometric functions. Now, trigonometric functions are important because so many of the phenomena that we want information about are periodic, such as heart rhythms, earthquakes, tides, weather, and much more. It is known that continuous periodic functions can always, that's right, always, be expressed in terms of sine and cosine. The derivatives of sine and cosine play a key role in interpreting periodic change. So, let's get to it. I'll have my Superboy Owen assist me in these lessons. Let's see if we can find him.
Okay, with the introduction of chapter 3.2, I will show you how f of x, f prime of x, correction, might fail to exist. This following equation is going to be greater than any superhero that you've seen earlier. Greater than the Wonder Twins, Batman,
False.
Robin,
False.
Thor,
False.
Captain America.
False. Because Batman and Robin are DC comics, they're not Avengers.
So, as I was saying, you have f of x minus f of a all over x minus a. This equation right here is like the Holy Grail. This is the equation you need to have down to be able to complete this chapter 3.2. Okay, so here we have one example where the function fails to exist. This one so happens to be a corner. So if we were to take the derivative of this function, f of x equals absolute value of 4x, we would get a line at -4 and 4. And since they don't match up, it shows that the function is not continuous. The second example of where f prime of x might fail to exist is with the equation f of x equals x to the 2/3, which gives us a cusp, which is where the slopes of the secant lines, one side approaches positive infinity and the other side approaches negative infinity on the xy plane. So here we have the third example of how f prime of x might fail to exist, with the example of the tangent line, with the equation f of x equals the cube root of x, or the 5th root of x, or the 7th root of x. One more. The 9th root of x. I hope you see the pattern going on here. So anyway, with this equation, the vertical tangent where the slopes of the secant line approach either positive infinity or negative infinity will from both sides. In this example, it's positive infinity. The fourth equation I'll be showing you of how f prime of x might fail to exist at f of x is with the discontinuity u of x equals -2 comma x is less than 0, and then 2 comma x is greater than or equal to 0, given by this graph showing this. And so then, by using the function, the limit as h approaches 0 from the negative side, we have -1 minus 1 over h, using the equation we had earlier that I showed you. I hope you listened. The next step would be the limit as h approaches 0 from the negative side equals -2 over h equals infinity, which shows in the example of how the left-hand derivative fails to exist. Okay, so for your first homework problem, I'll be giving you the equation.
We will be giving you the equation.
Y equals x to the 2/3. Tell us what type of graph this is. You can pause the video now to figure it out what type of graph it is.
And whether or not it is differentiable at all points. Have fun. Think hard.
Oh. Anyway, did your equation look like this?
What? It's a graph, not me.
Oh. My bad.
It's bad.
My bad. Thank you. If it didn't, please pause the video and correct your graph. Now that you fixed the graph, what would we call this graph? Yes. Jeff.
Cusp.
That is
Oh, Jeopardy. What is a cusp?
that is correct. A cusp. In this homework problem, the second one, I want you to prove how this equation fails to exist.
Graphs, please.
With u of x equals -2 when x is less than 0, and at 2 when x is greater than or equal to 0. You can pause the video at any moment.
So, you done?
Alright. Did you use that equation I showed you earlier? The Holy Grail,
Did ya?
the Thor, the Iron Man, greater than Batman, the equation f of x minus f of a all over x minus a. Using this equation, we can plug these into this.
I'll get busy on the graph. Keep going.
Oh, okay. So anyway, you have -2 minus 2 all over h. once you have this, it shows the limit as h approaches 0 from the negative side is -4 over h. Thus, the limit as h approaches 0 from the negative side is infinite. Did you get that?
Negatively so.
What? No, Jeff, it's not. No.
We'll just cut the video.
Why would you do that?
We'll cut the video before
Okay.
then. Because there was a pause.
What's from 0 from the negative side? Like -2 over h is positive infinity.
We good.
So, for your third and final homework question, you'll be given the equation, and I want you to tell me what type of graph it is. So, you have 3x minus 2 absolute value of x minus 1. Given that equation, tell me what graph it is. Go ahead and pause the video.
So, what'd you guys get for your graph?
I marked on myself.
Well, this one, Jeff, what would you say? It's a tough one?
I think this one's a little tricky, but if I had to choose what type of grass it would be, I would say a corner.
Why'd you say that, Jeff?
Well, I mean, me, just personally, I can like look at any equation and just graph it in my mind and visualize it. So I'm really cheating. But, I mean, for like the lesser folk, probably the absolute value is a good giveaway.
Really? Can you?
I can.
Oh!
Watch. Like this one, -1, gonna hit down here and expand a little bit faster, and boom, that's a graph. That is your graph. It's a little right angle right there. And that's geometry.
And what would you call that graph?
I would call that the graph of this.
Okay, so here we have a corner. Could you move out of the way from the camera?
I'm not in front of the city. That looks like a corner.
It's an O. Hold on. C-O-R-N-E-R. Why would you say that looks like Connor?
Who were Connor's able to be?
You serious?
Hey guys, good to see you again. Well, I think that we should get down and dirty into this stuff. So I'm going to show you how originally it was proven what the derivatives of the trigonometric functions were. And they're all solved in the same fashion. So I'm going to walk through the sine one, and then we'll go learn what the rest of the 6 are, and then we'll have some fun with them. So let's go to that one. So to find the derivative of the sine function, use the original definition of a limit to find where the actual slope is, because limits, derivatives, slopes, they all kind of intermingle. So we set up our equation of dy dx equals a limit as h approaches 0 of sine of x plus h minus the sine of x all over h. Now, our next step, the dy dx is the same, so we'll just bring that down. Remember to always have that in. Miss Jackson will dock you points if you forget it. And then we'll have the limit is still the same, so that will come down also. But then, this is where it starts to change. And using the angle sum identity, what our next line is going to be the sine of x times cosine of h minus cosine x sine h minus your original sine of x. And it's all over that h. Sorry about that h, guys. Alright, so that's our second problem. Well, that's our second step. Now, we get into the real fun stuff. Bring down our other equal sign. Let's get that going. And then we get the sine of x, which is right here. And then cosines and sines are pretty much, they're almost complementary of each other, you could say. So when you subtract cosine from 1, you'll get the sine of x, and vice versa, and they just fit together nicely. So we'll have sine of x times cosine of h minus 1 to get to that sine of x. And then we'll have that plus cosine of x sine h. Again, all over our h. Now, we have to separate this into a bunch of different things, but essentially what we'll be doing is the limit as h approaches 0, and we'll be breaking it up into sine of x times limit as h approaches 0 of cosine of h minus 1 over h plus the limit as h approaches 0 of cosine of x times the limit as h approaches 0 of sine of h over h. That seems pretty complicated and wordy, but it really all boils down to is we have sine x plus 0 and then plus cosine x times 1. And, oh sorry, this is a multiplication sign. And anything times 0 cancels out. Anything times 1 is itself. Bring down our equal sign. The derivative with regards to x of the limit, it equals the limit as h approaches 0 of the cosine of x. Therefore, derivative of sine is the cosine of x. Now, that seems like a complicated way to get there, but once you remember it, it's easy. Derivative of sine of x equals cosine of x. Now that you've seen how we do that, I'm going to take you to my little cheat board. This will make things a bit easier. Here, we have all 6 of the basic trigonometric functions. We have the derivative of sine of x equaling cosine of x, which we just so proved. Derivative of the cosine of x, which equals negative the sine of x. Derivative of tangent of x equals secant squared x. The derivative of cosecant of x equals negative cosecant x times cotangent x. And the derivative of secant x equals secant x tangent x. And finally, but definitely not the least important, we have the derivative of the cotangent x equaling negative cosecant squared x. Now, remember these. These are going to help you in every single problem that we come across in section 3.5. These are your friends here. These are the Wonder Twins. the superheroes, the Justice League, the Avengers. This is all of them. Remember these guys. Let's do some problems. So, for our first example, we're going to find the derivative of x squared times the sine of x.
Huh. Looks a lot like the product rule, Jeff.
You know, it is the product rule.
And you know what the product rule is, Jeff?
It's slipping my mind.
Well, that's weird, because it would be the normal x squared times the derivative of sine of x plus 2x times sine x.
Okay, let's get to it. So, as Owen so wonderfully stated, our first step, we're going to leave the first term alone. Would you like to write that one up for me, Owen?
Oh, yeah.
Thank you. Now, we multiply that left alone term by the derivative of the second term. And as we learned from the previous lesson, the derivative of the sine of x is the cosine of x. So we'll multiply this x squared by the cosine of x. Now, what was the next part of that product rule?
Plus.
Okay, so we'll add. Now, we're going to leave the second term alone. So we need to find the derivative of the first term. And using those fancy rules that we learned back in section 3.1, we can just do it really quickly. Bring down the exponent, subtract 1 from it, and we're going to get a 2x. And then multiplied by the left alone second term, and we have sine of x. Therefore, the derivative of x squared sine x equals x squared times the cosine of x plus 2x sine x. See? It's not that bad.
There you have it.
So, the first example wasn't too bad, but not everything is always quite as simple. So, for our next example, what we're going to find is the second derivative of y if the original y equation is a secant of x.
Round 2.
Here we go. So, first of all, we're going to find the second derivative. Obviously, we got to do the first derivative. So, Owen, you want to do this one for us?
No, not at all.
Alright, I'll do this one. So, our original derivative, or y prime, f prime of x, dy dx, however you want to write it, it's tomato at this point, equals, and from those rules, the Wonder Twins, Avengers, you know, those guys I showed you, the derivative of the secant of x is,
No idea.
well, Owen didn't pay attention like I know you guys did, but the derivative is going to be secant x times tangent x.
Oh, that's right, you showed us earlier.
Yeah, that was the one that was like located right around here. But anyways, so we have the first derivative, but what we're looking for is the second one. So, product rule. How about that? You guys ready? You ready?
Yeah.
Let's jump into this one. Alright, so y double prime. So, the product rule again. Owen, what was the product rule?
The derivative of the first function times tangent plus, keep the first one alone, times the derivative of the second.
Very good. You guys gotta remember that one too. That might pop up a lot. So, what we have is left alone function, secant of x, times the derivative of our second, which again, if you remember the rules and the cheats that I showed you, the derivative of tangent is secant squared of x. So, multiplied by the derivative of tangent, secant squared x. Now, plus, and then, since we left this one alone the first time, we have to take the derivative of that one this time. So, we have secant x, tangent x, which is the derivative of secant, multiplied by the left alone second term, times tangent of x. So, at this point, this technically is a correct answer, but, you know, why not simplify? Life's too complicated. It's like a slap chop, just let's go simpler. Alright, equals this one times this one, 1 plus 2, essentially 3. I'm going to call it secant cubed. I don't think I'm breaking any rules here.
He's not.
So we have secant cubed plus secant x, tangent x times tangent x. These two appear to be the same term.
They do, Jeff. They really do.
So, I'm gonna guess that we could, do a little simplifying here and call this secant x tangent squared x. We'll just put that in parentheses just so it's a little easier to see. And there you have it. The bread and butter, the goat and the maid, the swan and the golden egg, the peanut butter and jelly, the Chinese food and General Tso's chicken. That, this is the thing.
Buddhist delight.
That's not what this one is. But double derivative of y. The original equation is secant x, secant cubed x plus secant x times tangent squared x. Well, this is going to be our last example before we get to the homework problems. So, if you guys have any questions, tough.
Don't ask.
Well, without further ado, let's get going to our last one. The last example problem is find dy d Jacob of y equals the cotangent of 77 Jacob.
Wow, Jeff, I've never seen this problem before.
This one is a wowzer. It's got a trick step, got an icy patch in it. It's the whole package. It's the whole package.
Never seen done.
Well, alright. Hang on to your tinfoil and tennis balls and let's get after this one. So, this one may look daunting because Jacob is a formidable opponent. But you just gotta remember, he's basically an x in this point. He's just our variable. So,
He is.
we essentially have just y prime
Easily removed.
of the cotangent of 77x. So, what was, you guys remember our derivative for cotangent? Of course, you guys are better students than that. We have
AP.
negative the cosecant squared of our inside, 77 Jacob, times derivative of the inside, 77. So, simplify that up a little bit. We have negative 77 times the cosecant squared of 77 Jacob.
Wow. Is that it?
That is it for examples.
Just the Winston Devil right there.
Well, let's jump into those homework problems. See you on the flip-flop later. Okay, class. First homework problem. We've got find the derivative of tangent of x over cosine of x. Now,
That looks tough, Jeff.
I mean, quotient rule, got some division in it, so maybe throwing you for a loop, but promise you, it's not that tricky. You guys can do this. I believe in you. 5 gold stars to whoever gets it right. Let's go. The clock starts now. Okay, so we're back. Hopefully you guys had time to finish. If not, try to finish up while we're starting. Alright, so first glance at this, we have division going on. If you're finding a derivative and you find division going on, what would your first logical step be, Owen?
Quotient rule!
That would be, just looking at quotient rule. But let's delve into this a little bit. Because if you guys remember, tangent of x is really the sine of x over the cosine of x. and then that again is divided by cosine of x.
Wow.
Now, you can't have a fraction in the denominator, so you flip it, put it on the top, and you really, these will cancel each other out, and you just have the sine of x. Does that look a bit more simple than that?
A bit.
I mean, especially with those
Just a
awesome
little.
rules that we learned.
That you taught us.
Yes.
That were on the board.
This-
Because of the Avengers, we were saved.
Thor saves the day again. So, we go from like dividing and all this nasty squared stuff to a one-step problem of the cosine of x. Did you guys get that one? Make some noise. Applause meter maybe.
Wait, Jeff, you have sine of x, and then you have cosine of x.
Yeah.
Oh, because it clearly equals. We'll
Yeah,
just cut it
because
out.
this equals the sine of
it's
x.
done. It's done.
And yep.
Right. It's playing.
Well, this one's not quite as Owen's leaving me. And he's back.
Oh, you too.
So, for our next homework problem, this one doesn't really quite have a loophole like the last one, but we're back to that product rule that we've known to love.
We have.
It's a love-love relationship. It's just, yeah. What can I say? I love it. I don't even know another word for it.
Do you?
Let's just get to it.
Love.
There's enough banter. So,
Warm.
we're going to find the derivative of the cosecant of 2x times the tangent of x.
We?
We. You.
Them.
Us. So, well, this is a time where we cut you loose. So, take a few, work it out. You know, let's see where time takes us.
So, whoo! I hope you enjoyed that nice
Woo!
fire. As you can see, we have the cosecant of 2x times tangent of x. If you're anything like Jeff, you have used the product rule, which he loves.
Woo! So, first step, we gotta leave the first term alone. So, we're just gonna rewrite that bad boy.
Ooh.
Now, we gotta multiply that by the derivative of our second term. And using those fancy little rules that we learned, anybody remember the derivative of of tangent x? Almost give it away. Yell it out. Yell it out in class. I really hope somebody did, because this would be really awkward if it's really sound.
Jacob!
Alright, so, yeah, that was it. Secant squared of x.
Nice job.
Now, we have to find the derivative of the first term.
Ooh.
Well, this one
What?
might not be
don't know about that one. Are they that? They are AP. You must understand. You're bad.
My bad.
You're bad.
So, what we
Come
got?
on.
We're gonna, yeah, you guys know what it is. Negative 2 cosecant of 2x times cotangent of 2x. And we gotta multiply that, though, by the left alone second term. Which, you guys remember, your AP, as Owen likes to say. Tangent of x. Now, I want you guys riddle me this.
Rhyme.
Is this the answer that you got when you worked it out? Is this the answer that you would tell your kids if they were to ask you what the derivative cosecant of 2x times the tangent of x is?
He's trying to say, is this the correct answer?
Would you swear on a Bible that this is the answer you received?
Is it the correct answer? Yeah, I don't know why it's doing this.
Let's take a moment. Just right there. I'll tell you how I became I'll tell you the story of how I became the Prince of Bel-Air. Time together and learned, laughed, loved. Well, I mean, calculus is what makes the world go round. It brings us together. It's what keeps Owen by my side. It's what, I mean, what doesn't it do? But until next time, this was Calculus with Jeff and Owen. See you next time. Bye. Not a sour note in the bunch, Owen. Not a sour note in the bunch.
Oh, you tease me.